Hello, everyone. Good afternoon. My name is Tobias. I work for National Oceanography Center. I'm a research software engineer. And together with Colin Soze, I will present today enhancing real-time geospatial big data processing and presentation through cloud-optimized storage and formats. So I work at NOC, and NOC, like any other institutions in the UK, operates global ocean models to predict various oceanographic variables. And these models generate daily extensive data files, normally multi-gigabytes or multi-terabytes of file. And the most common file format that scientists like to work with is GRIP and NetCDF. So the normal approach that most of the institutions follow is to run, they run the models in some HPC system, and then they store they get the output of the raw output from the models. They have like a data conversion layer to convert that format to different types of other formats because they have several clients, so web applications, APIs, scientists, so they need to convert it to different other types of formats, and then they need to build different types of APIs and servers to make the data available to all the clients. So as you can see here, we have several challenges because we can have duplicate files, we need to use a lot of computational resource, so we need to try to deal with that challenge. So my idea today is try to present a new approach. So my idea is not to present something that's a silver bullet, but it's something that maybe it's useful for some type of project. So my idea is that instead of convert all the files to different formats, I would like to give an idea to convert everything to cloud-optimized format and store it in a easier place in a like an object store. And from the object store, scientists and web application can access the data directly from there. So I will show here, I will show each step and why I'm choosing this approach and why it's so useful and maybe useful for your institutions. So first I'll start with the data storage. So to store the data, I'm choosing to store the data in an object store. And object store is optimized for managing extensive and unstructured data. And model output is unstructured data, so it's perfect for that. And object store is cloud-based, so because it's cloud-based, it's scalable with increasing data demands, and it's also enable parallel accessing. So it's two things that's really good, parallelization and scalability. And it's really easy to access the data in an object store using the REST API and issuing HTTP GET requests. So in this project, we're using Jasmine Object Store that's based on AWS S3. Use the same API as AWS S3. So the format of file that I'm choosing to work with is ZAR. I saw several presentations that use ZAR in different types of scientific research, and I'm using ZAR here to deal with oceanographic model outputs. So ZAR is an open source format to storing chunked, compressed, and in dimensional array. So instead of saving your data in just one NetCDF file, one GRIP file, you save your data as an object, and each part of the file is saved in different types of chunks. So when you want to access the file, you don't need to download the whole data set. You don't need to download 1 terabyte. You can only download just the part of the file that you need, and you can also load and process it in a parallel way. So it makes things much faster and increase the performance. And it's also compatible with the most popular Python libraries like NumPy, Xarray, and Dask. So a scientist that knows how to work with NetCDF, for sure they will learn easily how to work with a ZAR file. So to process the data, I'm using Silk workflow to do all to run the model. We're using Silk workflow to run all the models, and in HPC, it's running on Archer2, and then you transfer everything to Jasmine, and on Jasmine, we perform the transformation, converting, reprojections, and upload the data on the object store. And because we are working with ZAR, we can apply parallelization using Dask, so we can increase the performance of that process. So now that you have all the data in the object store, how can the scientist and the web application can access the data? So if you're a scientist, you can access the data direct from the object store, just issuing HTTP GET request. So if you have the address of the domain, of the link, you can get the data from there. Like the same way like a NetCDF, so you can use Xarray for that, just 2 lines of code, one to import and one to load. But if you are using NetDF, you need to download the whole data set, and with ZAR, you don't need to download the whole data set. You only load the metadata, and from the metadata, you can only get the part of the file that you need, and together you can apply parallelization with that. So it's a real advantage for with ZAR files. But in a web application, it starts to be an issue because ZAR, it's a good format, but it's not that optimized to JavaScript. So it's better to have in the between an intervenient API to access the object store, send the data to the front end. So that's why I'm suggesting here to using a dynamic tile server that works as an intervenient API. So the dynamic tile server, it's responsible to interact directly with the object store, get the part of the file that you need, and generate the tiles, the images on the fly, and send the image to the front-end applications. So instead of generate millions of tiles like you have to do with GeoServer, we can do it. We can generate the format, projections, and style on the fly. So it's based on T-tile, X-array, FastAPI, X-array, and real-time and Rasterio. So from the front-end application, we make an API request to endpoint, send Z, X, and Y is the position on the map. And the workflow on the back end, it's open the ZAR metadata, verify the position of the part of the file that you need. It converts it to an image in code, in this case, it's PNG image, and send that image on the front end. And from the front end application, you see the image on the map. So, and one thing that's important, so to increase the performance, we are running here in a serverless environment, as a serverless application in a Kubernetes environment, and we add together in the Kubernetes a caching layer using Redis to enhance the performance and remove a little bit of the pressure from the backends. So from the web application now, it's just an API, we can build like a static website. So you can, if you only know front end, you can build a static website on the front end and just access the API, or you can also build a dynamic website using Python. So I'll show here a live demo. Hope everything works fine. So this is a React website that I'm interacting with my object store. So, and I will open here like a 5 GB ZAR files. It's a Salinity data. So it's in the back, I'm just sending a request to the backend, and the backend sends to me the tiles for me, so the part of the image. So you can see that 5 GB of file or image is loading really fast on the front end. So I can change the color, for example, just to show. And it's a good thing that you can change the style while you are rendering. So to render again and show the data again in the front end. So yeah. And another approach that I want to show, I built a Streamlit website that it's everything in Python, so I don't need to write JavaScript. So in Python, you can, for example, select interact with the object store. I have several data here, and I can open the same data set and plot it using Plotly or Cartopy. Or even Leaflet. So in the case of Leaflet, I'm using I'm accessing the tile server to plot the data here in the front-end application. So let me turn to the presentation. So I'd like to thank some people that helped me in the presentation, João Morada, Adam Blake, and Andrew Corward. I think, let's return to the slideshow. And here are the links for the GitHub repository for the tile server, the React applications, and the data conversion NetDF to ZAR. So everything is available and open source. So thank you very much for your time.
Thank you, Tobias. That was perfectly 10 minutes. Please do submit any questions on Canopy. And I'll start us off with a couple that have come through already. One, ZAR is sounding really interesting. Thanks for sharing it with us. Do you know if it works within Fortran? Often we're transferring data between large models and Python, or alternatively, do you know if we can easily convert a netcdf to a ZAR file?
Using Fortran or?
I think so can you use ZAR in Fortran, or as an alternative, if your model's outputting netcdfs, can you then convert them into ZAR?
Yes, it's easy to convert to ZAR. It's not easily, but it's easy to convert ZAR netcdf to ZAR in Python. I'm not sure if it's possible to do with Fortran. Maybe someone can help me on that. But the difficult part is how you want to range the chunks, because the way that you range you configure the chunks will affect everything. Will affect if you want to show the data in a front-end application, if you are a scientist that want to apply statistics. So I share here one of the repositories that I share here. There is some codes to show you how to convert data to netcdf to ZAR. So if you want to talk to me later, I can send you the link.
Another one we've got is, does the tile server work with arbitrary CRSs?
The tile server, the problem with tile server, that's, I'm not sure what's the meaning of arbitrary CRS, but I need to work with plates career, and the CRS that I'm using 4326. So I think it's possible to work with other CRS, but the most important part is that you need to work with regular grid data. So it's not possible. So if your model output is not in regular grid, you need to reproject it to regular grid. So in this project, I'm doing that. I need to reproject and then convert to ZAR and save the object store.
At least it's a familiar problem. So I've got one from Sarah here asking, who are the main users of your website?
The website now is still not available, yes, but the idea is that it's a new approach that we are trying to implement. Yes, we have some user at NOC, just internal clients, but the idea is that in the new project that NOC are working together, it's become to be a start of a new platform that NOC will develop in the future, yes. But right now it's just internal user, just internal users.
Cool. It looks like that's everything that's come through. So if you could join me again in thanking Tobias one more time. And thank you to all our panelists and speakers this session. I believe we're staying here, so talk among yourselves.